A week is 10% of this course. That's insane to think about. After today, this course is half over. That's kind of obnoxious to think about. I wish Oregon would go to semesters. I know you don't. But anyway, regardless. It's an old idea called average rate of change. Average rate of change. Why did I make some of those letters so large?
Alright.
So we can use an acronym, because I'm going to get tired of writing that. AROC. Average rate of change. Remind me what average rate of change is again. Well, it's AROC, yes. But remember what it is. We first mentioned this. We first mentioned, I think, with grade. I could be wrong about that. I know we talked about it with linear modeling, though. Average rate of change.
Find the middle of the change, right?
Say that again.
Finding the middle.
Oh, good. I like the middle idea. Oh, I like the middle idea. The middle idea, because we're looking at that average, right?
Yeah, the average.
So let me ask you a question. I'm going to tell you a story, actually, that'll tie, I think, what Randall's talking about. Years ago, there's this road called the Jersey Turnpike. If you've ever seen Being John Malkovich, it's got a big part in that movie. It's funny. He gets flushed out on the Jersey Turnpike every once in a while, if I remember correctly. And there are these things called tolls on the Jersey Turnpike, which I know is like an alien idea to Oregonians. Thankfully, it's an alien idea for Oregonians, because it's terrible. It's how things like the Turnpike make money for itself. And essentially, the way is you go through a toll booth, you get a ticket, and then you get off at another toll booth, and then you have to pay a certain amount of money based on how far you've come. And one of those, when you get the ticket issued to you, there's a timestamp on it. There's a timestamp on it. And what's interesting about that is, years ago, for a little while, the police departments in Jersey were using mathematics to give people tickets. So here's the deal. The speed limit at that time on this one stretch of the Jersey Turnpike was 60 miles per hour. Now 60 miles per hour is a wonderful, wonderful speed when you're trying to figure out how long it takes you to get somewhere, isn't it? Why? 60 miles per hour is 1 mile every minute. Right? 60 miles per hour, 60 minutes in a mile. If you cover 60 miles in 1 hour, you're going 1 mile per minute. That means you're averaging 60 miles an hour, yes? So what the cops were doing, this is genius. I'm going to make the math easy for us. Let's suppose that there are two exits in the turnpike that are 120 miles apart. Let's just make the math easy for us. They're not actually like that. Some of them are 36 and 42 miles apart. But suppose you pull a ticket at 11 o'clock at exit 1. And exit 2, let's make it the math easy, is 120 miles away. And the speed, the entire time, the speed limit is 60 miles an hour. If you got off the turnpike at 12:30, the police would then mail you a ticket. Because what had to have happened? Somewhere would have had to have happened. You had to have been speeding somewhere, because if you were going 60 miles an hour for 120 miles, it should have taken you at least 2 hours if you were going 60 the whole time, if you were averaging 60 the whole time. If it took you less time than 2 hours to get 120 miles, at some point you had to have been speeding. Does that make sense?
Yeah.
It's mathematics. Distance equals rate times time, yes? Distance, here we go. Distance equals rate times time. If the distance is 120 miles and the speed is 60 miles per hour, solve for t. T has to be 2. Yes? If t is less than 2, this has to be bigger than 60 to make it equal 120 miles an hour. Or 120 miles, excuse me. So they were issuing tickets based on this, which was genius.
Is that really illegal?
It's mathematics, it better be. It's why the radar guns that's why they use the radar guns. It's mathematics too. We're getting to the mathematics here. So they stopped doing it. And one of the reasons why is, well, I shouldn't say this is the reason why. Some of my friends found out about this and they said, I'll show them. So what they did was they get on at exit 1. They'd speed up to the rest stop, going about 80, 85, 90 miles an hour. Then sit at the rest stop, drink coffee and smoke, and then get off at exit 2, at least 2 hours later. Like, I got them. I'm like, how did you get them? You used more gas by speeding, and you smoked like 5 cigarettes, so you're shortening your life, too. I don't see how you're getting the cops. The cops stopped doing it. I think it became too hard to actually monitor the income from it, and they just went to the patrol sitting there, not hitting people with the radar guns in pairs. The Jersey Turnpike, anybody ever driven on it? It's a terrible place. It's a terrible place. I wish it on none of you, except for those of us that have suffered through it. So, but anyway, what does this have to do with average rate of change? Well, if you cover 120 miles in 2 hours, what is your average speed? 60 miles an hour. Does that mean that you have to go 60 miles an hour the entire time?
Yeah.
Nope. You could be going 100 miles an hour for some of it and then stop completely. Time's still running though if you're stopped. And this happens often on the Jersey Turnpike. You sit there, sometimes you feel like you're going backwards. And then you might creep along at 5 miles an hour for a while. And then you might speed up to 60 for a brief moment. You might never go 60 miles an hour more than a few times, but you can average 60 miles an hour, yes? That's why 60 is kind of a fun estimate to use. What I tend to use on highway travel in Oregon is I assume I'm going to average about 50 miles an hour. Because I know once you get to Idaho, it's like 75 in places and 60 in places. But you don't actually go that fast the entire time. You stop for gas, you stop to pee, you stop to get food. All those stops, and I kind of use like a lowball estimate of my average speed. Or maybe you don't, that's okay.
I don't like to stop.
Well, that's okay.
Idaho too.
Even though I don't have gas, I'm not stopping. I'll put my sail up if I have to. So that's what an average rate of change is. An average rate of change, simply put, an average rate of change is total distance divided by total time. That, my friends, is all we're going to use today. That equation right there. Average rate of, we're going to change it to instantaneous rate of change by the end, because that's what we're interested in. The average rate of change is going to be total distance over total. What are you thinking about right now? Just thinking. Oh, good for you. I'm sorry. I see the face change. I'm like, oh, I should quell that. Any uncomfortableness, I want to make sure we get addressed. So, what I want to first calculate is, well, I want to calculate a bunch of stuff today based on our model, because we have our model, which is great. Let's settle on a couple numbers right now, though. Okay? Let's say the time at the start and the time at the end. And let's agree on the distance at the start and the distance at the end. This is what I want to start. I want to agree on these right now because we're going to use these numbers the entire time. Okay? So we're going to have to use our data for some of this, but some of this we also just know because we calculated them yesterday. The time at the start, we're going to call that 0 seconds. Because that's when we said go and you all hit go. So we're going to call this 0 seconds. How about the time at the end? Now, let's jump over that for a second. Let's jump over that, no pun intended. Let's just jump over that for a minute. We'll come back to that one. How about distance at start and distance at the end? I think that would be 0 as well, even though the model disagrees a little bit. Remember what the model said my distance at the start was? Negative 0.37 feet. No. Remember, do we have a perfect fit parabola? Best fit. The best fit doesn't quite go through the origin. So this is not bad, friends. This is feet, yes? This is negative 4 inches-ish. I can live with that kind of error. Let's just pretend it's 0 for our calculations. So the distance at the start was 0 feet. I haven't gone anywhere. I mean, you could argue a 4-inch difference with just how I was rolling. That Pete was next to me. I was probably slightly inconsistent with the bike back and forth. So I thought, Pete, you're here. There we go. Slightly inconsistent. I tried to be pseudo-consistent, but I can let 4 inches go. Distance at the end? 200 feet. That's where my last group was clocking me with their watches, yes? So I know the entire trip was 400 feet of travel. Now what we got to do is we got to get an agreement on how long it took me to hit that 200-foot marker. Now I know the data, we entered a data point in there, yes? But I think this is a perfect place to actually use a little bit of mathematics. A perfect place to use this equation. And if that is 200, what is x? You see what I'm saying? If this is 200, which is the distance, what is x? So in other words, solve that equation, 200 equals this. Now, we're going to do it equation boot camp style. We're not going to do it with the quadratic formula. I don't think anybody likes that anyway. Like, I mean, whenever I mention it, they're like, oh god, it's the minus b thing. Yes, it is. But we're going to do it equation boot camp style. Graph. We already have a graph. Take a look at this. Let's pull this down. Once we get this, we'll take our 5. Then we'll play with it after the break. So, if you hit graph, there's my position. Changing as time changes. Yes? That's my position, changing as time changes.
What equals 200 then?
That's what I'm saying. All we got to do is figure out at what point does the vertical component of this graph hit 200. Yes, it's going to be close to that point. But at what point does the graph predict? It's not close. Will you say no? Not that. Well, let's find out. Let's find out where it is. So what you want to do is just go into your y equals and stick a 200 right there. Stick a 200 right there. And then just hit graph again. So what in other words is, here's 200, here's 0.
10.9.
It's very good, very good. We'll go back to that. From here, boom, to right there, it took me 10.9 seconds, according to my model. 10.29, so 10.3 seconds. We'll call it 10.3 seconds. Our data was 10.2. The model is predicting 10.3. That's perfectly fine. That's perfectly acceptable to be off by a tenth of a second. I mean, you could attribute tenth of a second error to the fact that we weren't all hitting the start button at the exact same time due to the speed of sound not being consistent. Speed of sound is pretty slow. How many of you guys have been very, very far away from, say, somebody swinging a sledgehammer against a rock and you see it hit and then hear it a fraction of a second later? Speed of sound is nowhere near as fast as the speed of light. So I can live with a 0.1 second difference. So that intersection point right there, that is what we need to find as far as the x value, and this is where that intersect command is going to come in handy. Intersect, first curve, yes, second curve, yes, guess, I don't care, let it find it for me. There we go. Model predicts 10.29, we'll call it 10.3 seconds to get from start to 200 feet. Damn close to our data, damn close to our data. So now we have an agreed upon end time. We have an agreed upon end time for our model. And that, my friends, that combined with everything else on that graph is all we're going to need to figure out how fast I was going at the end. Cool? But let's take 5 right now, yes? Let's take 5.
Yes.
Let's take 5, turn the camera off. If you want to grab your papers, I got extra papers up here, you might want to root through those.